Okay, so today we'll be talking about simple code generation. Okay, so far we have covered parsing, so we know how to do parsing, and we know how to construct the abstract syntax tree, and we talked about how to go from an abstract syntax tree into actual code. So if we have an example like this, we will focus on expressions today. A times 3 plus b. The abstract syntax tree for this is going to be like plus is equal to the multiplication of a and 3, and then you add this to b. So this is the abstract syntax tree. Now, in terms of code generation, we talked about this. We talked about how we can generate code for this. Today we will talk about it in greater detail. We will think about all the issues that are involved in generating code for an expression like this. And in today's lecture, we will concentrate on generating code for an expression. So in the next lectures, we will look into code generation for conditionals like if-else and loops. But today we will just focus on expressions, how we can generate code for expressions. So in this case, the code that we want, this is a variable, so we would like to load the variable, load a, and we want to load 3. So we will load a into some register, like R1, load immediate of 3 into some register R2. Of course, loading a here is loading a variable, which means a memory location, and that consists of a base and an offset in general. So remember the instruction that we used in the earlier lectures, load AI, load for address and immediate, where the base is in a register, A or ARP. What does ARP stand for?
Activation record pointer.
Yeah, activation record pointer. Exactly. So A activation record pointer, and then the address of A, and we want to put this into some register R1, loading immediate of 3 and putting this in R2. Then we want to multiply what? R1 and R2. And we want to put the result in some register R3. Then here we want to load AI R activation record pointer, address of B into some register like R4. And here we want to add what and what?
R3 and R4.
R3 and R4. And put that in some register R5. So now today's lecture is about the implementation details of this. Not the implementation details at the coding level, but at algorithmically. Because in the programming assignment, you will have to write code that traverses the abstract syntax tree and generates these instructions. So we will look into this. We will write pseudocode for this. Basically, our objective here is to write pseudocode for doing this. So how do you think that pseudocode will, what do you think that pseudocode will look like? So
This for a while.
yeah. So it's a tree traversal, and we said what kind of traversal will serve us well here? Depth. Depth. And by the way, why is it depth? Because in order to do this multiply, we'll have to calculate everything beneath it. Everything below the multiply has to be calculated. So we have to go in depth. We can't calculate the multiply until we have calculated everything below it. And same applies to every operation in this. So it has to be recursive. So what if we start, let's define a function expression, for generating an expression. And that will take a node. So it's going to take, so this is pseudocode. It's not actual code. So the parameter for this is going to be a node. And then it's going to switch on the type of the node. So there will be a switch on the type of the node. So here we are implying that the node is a data structure. You can think of it as a class or a struct node. And this node has some fields in it. One field is the type. And the type in this case is, for expressions, is going to be, there are 3 types here. What are the 3 main types?
Operator, variable, and
Yeah.
immediate value.
Yeah. So it's either an arithmetic operation for what we are limiting ourselves to at this point. It's either an arithmetic operation or a leaf, and the leaf is an operand, and this operand could be either a variable or a number, an immediate operand. So it's either an operation or an identifier, or let's call it a variable here in this context, because identifier makes more sense in the context of parsing, but here it's a variable. So variable is a better word in this context, or a number. Then we need the kind of operation. What kind of operation? If it's an operation, then we need to specify the kind of operation, which is add or subtract or divide or multiply. We need to know the operation. There are other fields. Now, as we write the code, we will discover what the fields that we need are, and then we will add them as we discover the need for them. OK. So node type. So let's first do the easy ones. If it's a case variable. If it's a variable, or in fact the easiest is let's start with the easiest, which is the number. So if it's the number, then all what we need to do is to issue a load immediate instruction, or to generate here in this context. We're not issuing, we're generating code. To generate a load immediate instruction. So let's assume that we have a function emit. We have an emit function that takes an operation, source 1, source 2, and a destination, and it knows how to emit the right instruction. So if this operation is load immediate, it will know that source 1 has to be a number, an integer, and the destination is a register. Source 2 is not used because for a load immediate, we only have one source which is the immediate value, and we have a destination, which is the register. For the load address immediate, the load that loads based on a register, a base, and an offset. So source 1 is the base, source 2 is the offset, and the destination is the register that will receive the result of the load. Okay, so here, this is source 1, this is destination, this is source 1, this is source 2, this is destination. And for the add, this is our source 1, this is our source 2, this is our destination. Okay? So we have this, we assume that we have this clever emit function that will emit the right code. So in this case, we will call it, if it's a number, we will emit a load immediate, and the first source, so we need to give it the number. So where will the number come from? So now you are working on your assignment, on the programming assignment, and you have constructed the abstract syntax tree, but you need the number.
Value will be.
So in this node, should also have a field that stores the value. We are using a generic data structure, by the way. There are other ways of designing this so that you can, for example, you can have a base node class, and then you derive from this base node class different derived classes for the different types of nodes. An operation node is different from an identifier node, is different from a number node, because each type of node is different. And if you want to do this, if you want to design this properly, you will have a base class for the node that has everything that is common to all nodes. And then in the derived classes, you will have whatever is specific to that particular type of node, such as an operation or an identifier or a number. But here, we're not going to worry about this, so we'll put all the fields that we need, we'll just put them in one data structure for now. Okay, so we need a value, exactly. So when we create now, you should start thinking, when you are creating this abstract syntax tree, then in this node, when it's a number node, you need to store the value somewhere. So now we need this load immediate. Our source 1 is going to be node dot value. Source 2 is going to be null for the immediate, for the load immediate. And our destination is going to be a register number that will receive the destination. Now the question is, what should that register number be? Look at this abstract syntax tree and the node that the code that we would like to generate. So we have these destination register numbers. So where do you think these will come from? If you were writing the code to implement this, where will the, here we put R1, here we put R2, R3, R4. So where do you think these should come from, these register numbers?
Well, assuming you have infinite registers, you would just want to keep track of what you've already allocated, and so you would take that at one.
Yeah, exactly. So exactly, all what you need is a counter. And remember that at this point we are doing only virtual registers. So when we are doing virtual registers, we can have as many registers as we want. So all what we need is a counter. So just we need a function that gets the next register number. So if we have a function that get next register, this function is going to return the next register number. So the first time we call it, it's going to return 1. The second time we call it, it's going to return 2. Then it's going to return 3, and so on. So all what you need is a counter, because these are just virtual registers. So we will just call this thing. So our t equals get next register, and it will return a t, and we will pass it here as a destination. And then we break for this case. So this is what we need to do in order to generate an immediate. Now to generate code for a variable, so what we called it variable. Okay. For a variable, well, again, since now we know that we need this emit operation, and we need a destination. Now the base and the offset for this are going to come from where? So to generate code for loading a variable, we need the base and the offset. And where do you think these will be? We can store them in this data structure as well. So we can store the base and the offset. So again, we can do t equals get next register, and we can do emit of load address immediate. Source 1 is going to be node.base. Source 2 is going to be node.offset. And the destination is going to be the t. And we break. So these are the leaf nodes. Now what about the internal nodes, which are operations? Case operation. Now when the node is an operation, now things are more, we need to do more than just issuing an instruction or generating an instruction. So now think about this. To generate code for this, what do we need to do?
Look back at previous registers that were allocated and then put it into a new register.
Okay, so we know how to get the next register number, but we need to, before we can calculate the multiply, we have to calculate everything that is below it. So this has to be done, and this can be a huge tree. So in this example, we only have 2 nodes, but in general, if you have an op like this, the left child, this can have a whole tree below it, and this can have a whole tree. Generally speaking, for an arbitrary expression. So what do you think the right thing to do is here? Because this can be any complicated expression, and this can be a complicated expression as well. So what should we do here at this point when we are generating code for this? So what's the right thing to do? Yes?
You have to make sure that each of the child trees are evaluated first.
And how do you evaluate them?
You have to go down.
Okay. So what should I write in terms of code?
Oh, expression, and put the left node and then the right node.
Yeah, exactly. So I should call expression recursively.
Yeah.
So this is recursive. So this is an expression at this level. Before I can compute this, I have to compute the expression for the left-hand side and for the right-hand side, and put each one in a register. Well, the register that receives the result of this. Okay. So okay, so I have to call expression of. Now, how do I get to those nodes?
Node.left, node.right.
Yeah, exactly. So I have to store the left and right as well. So we are discovering, the fields that we need to store in this node data structure, and this is something that you will be doing in the assignment. Okay. So expression of node dot left, and we put this into, let's call it T1, and T2 will do expression node.write. Okay. Now this means that whenever I compute an expression, I have to return the destination register, right? So it's in every case I have to return the destination register so that the node, the parent node, knows this. So expression for A should return R1. So this will become a return value from the left child for this parent. So the parent looks at the left and the right, and each one of them should return. So this means that this expression must return the register that has the value, the destination of this. So in this case, we will just return T. So now our T has to have the destination T equals get next register. So this is the T that will, or maybe we should call it result. That's going to be more explicit. You can call it T, that's fine, but if we call it result, it will be more explicit. Okay, I'm going to call it result, but it will be a more descriptive name. So this is a result, result, and result. And we return the result at the end. So return result. To make sure that everybody understands this, we're going to trace it. We're going to do a little bit of tracing after we are done.
Yeah, you're going to have to initiate another switch statement to handle all four of your operators. Or in this case, the two for the example.
Okay, so where are we doing this? We are assuming that this emit function is intelligent enough, is smart enough to to generate the right code for the operation. In fact, it's the only difference is going to be what that operation is. It's add or multiply or subtract. Everything else is going to be the same. So we're sending this to the emit function, and the emit function, we give it an operation, source 1, source 2, destination, and it knows how to generate the code that we want. Now, so we evaluate the left, we evaluate the right, and then we get the register for each one, and then we get the next register. Oh, I missed the most important thing. Well, I missed an important thing here, which is what?
Emit.
Yeah, emitting. So we have to emit, in this case, emit. What's the operation? The operation is whatever this operation here, the operation dot op. Yeah, so it's this is the op field in this, the actual operation name, or you can call it op name. So this is the operation. I send it to the emit, and my source 1 is going to be T1, my source 2 is going to be T2, and my destination is going to be the result, and then I'm going to break. And at the end, I return the result. Okay? And here, what are these T1, T2, and T result? In fact, these can be integers. When you work on this in the assignment, you will realize that these register numbers can be just integers. Okay, so now let's trace it on this example. So if we trace it on this example, we start traversing the tree from the root, right? So we start from the root. And in the beginning, so let's put the stack. So first we call expression on root, so expression on plus this node. Now expression on plus is going to switch, is going to go, okay, this is an op, so it will recursively call itself on node left. And node left is going to be the multiply, so it's going to call expression multiply. Now in expression multiply, it's an op again. Now it's going to call the left, its own left. The left of op is going to be this, expression of A. So we are going now on the stack. What we have on the stack is the leftmost path in the tree, expression of A. Now when we get to expression of A, it will identify A as a variable, and it will generate this, with register number 1 being holding the result. This will be the first time we call get next register. Get next register, and this will give us R1, and it will generate this instruction that we want. Now when this returns, when load A returns, we will be at this point in which function? In which?
The multiply.
Yeah, the multiply, exactly. So we're tracing the recursion here, because it's important to understand that this whole thing is recursive. So when expression A returns, it's going to be at this point, and we are in expression of multiply. Now the right-hand side of multiply is going to be the 3. So it's going to call expression of 3, and when we call expression of 3, it will load immediate the 3, and it will put it in register number 2. Now, and this will complete. Now we are in expression of multiply. So at this point we are in expression of multiply, and we are here. We finished this. This returned R1. This returned R2. And now it's going to get the next register. The get next register is going to give it R3. So this will generate this multiply that we want. So it's going to multiply R1 that came from the left child, that holds the result of the left child, R2 that holds the result of the right child, and R3 the new register that we have just generated. So it will generate the multiply R1, R2, and put the result in R3. Okay. Now all of this is in the multiply. Now the multiply will eventually return after this. Now it will return to the add, and now we are at this point in the add. So now we are here, but now we have returned to the add, the top level. Right? Now the left child returned, and the left child for the add returns what?
R3.
R3. Yeah. So it will return R3. Now it will call its right child, and the right child for this is the expression of B. And expression of B is going to do the load immediate, and it's going to return R4. Now at the add level, at this node's level, get next register is going to return what?
R5.
It's going to return R5. It's just a counter. So then we will emit the instruction, add R3 and R4, and put the result in R5. Okay. So this is how it works. So let me ask some questions now to make sure that everyone understands how this works.
Seems
oh.
simple enough.
Yeah, so it's simple if you master recursion. So if you are comfortable with recursion, then this is, this should be very intuitive. And DFS is an example of a recursive algorithm. Now, okay, question. If I if I move this result, get next register, if I move this here, will this work or not? Will it work correctly or not?
No.
No?
Okay, I think it will work correctly.
Yeah, it still work correctly.
But what will happen? What difference will?
Yeah, it won't be in the order, the register allocations won't be in the order that we showed here in the example. They'll be different.
Okay, so it will be different register numbers will be used, but it will be correct. So how different will the register numbers be? So what will happen to the register numbers? So let's renumber the registers. If we just do this.
It'll put, well, the first one in the add, it'll put it instead of R5, it'll set the destination to R1.
Exactly. So the destination is going to be R1. So basically, it's going to do the allocation for the destination in pre-order, not in post-order. But that's fine. These are just register numbers. So it's going to set the destination to R1, and then it will call the left child. The destination for the left child is going to be R2.
Right.
Okay. And here,
It'll be R3.
this will be R3. So now the left child for the add is going to be R3. The right child is going to be R4. Right? And then we will return to the add. Then this is going to be R5. So this will be R2 and R5 and put the result in R1. So it will be assigning register numbers in pre-order instead of post-order. But these are just numbers because these are virtual registers anyway, and it doesn't matter. So this will still be correct. Now, what if we move the emit here? So what if we do the emit? Well, no, not here, but the emit. Or let's move the emit and the result. Okay, so if we move the emit and the result here before T1 and T2, before calling expression. So if we do them in pre-order,
Won't work.
yeah, this won't work. So basically, getting a register number is not a big deal. We can do it before or after we compute the expressions below the current node. That's fine, it's just a number. But calculating the actual expressions below that and computing them must be done before we can generate code for the current node.
Yeah.
Because this is dependent on these. Okay? So the actual computation has to happen in post order. But the numbering of the registers, it doesn't matter. You can do it pre-order, post order, or any order. Okay? Any questions on this? Yes?
In fact, if you had put the emit before evaluations of T1 and T2, you'd be using the previous registers that were used, T1 and T2, from whatever operation was done prior to that, right?
Yes, yeah, but it will be wrong. Yeah, the T1 and T2 will not even have correct numbers. Yeah, so it's so it will not work.
Assuming T1 and T2 were global, because it's a recursive call and those are local variables.
Yeah.
So you would actually be putting garbage into that function at that point.
Yeah, you
Yes.
would, because it wouldn't be initialized. It would be whatever's in those locations at that time.
Yeah, but even if you find a way of, if you can number them any way you want. You can say, okay, I want the result of this node to be in this register. So you can find a solution for the numbering problem. but you will not find a solution for the actual dependence problem. Okay. Any other questions?